In this video, we'll analyze the data from the redox titration. We titrated the purple potassium permanganate with it was store-bought commercial hydrogen peroxide. The bottle says 3% hydrogen peroxide. We're going to see if that's right. First thing we got to do is balance the redox reaction using the half reaction method. Now you can kind of figure out what ions go together to make the two half reactions. But eventually in number 2, we need to know the element oxidized and the element reduced. So we might as well go through and assign oxidation numbers. Okay, so I'm going to have my manganese and my oxygen. I'm going to start with the oxygen because I know it's almost always a -2. There are 4 of them, so that gives me a -8. Because the ion is -1, the manganese must be a +7. Then oxygen is almost always -2, but there are 2 times when it's not. One of them is in peroxide, where a hydrogen is a +1, always a +1, unless it's neutral, which then means that my oxygen must be a -1. The manganese ion is just +2, +2, 2+, that's its oxidation number. And the only other time when oxygen is not -2 is when it's all by itself as a diatomic element. Then it's a 0. So now I'm looking for, let's hop to number 2, the element oxidized and the element reduced. And I'm always thinking oil rig. Oxidation involves losing electrons. If you lose electrons, your charge is becoming more positive, less negative. That must be my oxygen. In both cases, it's going from a negative to 0, either -2 to 0 or -1 to 0. That must be my oxygen. Oxidation involves losing electrons. Reduction involves gaining electrons, so my charge becomes more negative or less positive, like the manganese going from a +7 to a +2. Manganese. So you're obsessed with oil rig. Oxidation involves losing electrons. My charge is becoming more positive. Reduction involves gaining electrons. My charge is becoming more negative. Now I for sure know the 2 half reactions. I'm going to have the manganese as part of the permanganate ion, forming the manganese +2. There's 1 half reaction. First thing we do is balance the manganese, which there's 1 on each side. Next, we balance the oxygen by adding water. I will need 4. And then because this was run in an acidic solution, we didn't think much of it at the time, but you did have to add a little bit of sulfuric acid. There are hydrogen ions present, and I can add hydrogen ions then to balance out the hydrogen from adding the water. I will need 8. Hydrogen ions, 8 on both sides. Last thing we do is balance the charge by adding electrons, only electrons. So it looks like on the reactant side, I'm going to be a +8 and a -1. So I'll have a +7 versus a +2 on the product side. And since I can only add electrons, we're going to have to reduce this reactant side. Let's say 5. Now that gives me a +2 and a +2. Halfway there. The other half reaction must be my hydrogen peroxide going to oxygen. This time I don't have anything besides hydrogen and oxygen. My oxygen are balanced. There are 2 on each side. So all I got to do is add the 2 hydrogen ions. And then finally balance the charge. My reactant side is neutral, so I'm going to have to bring this product side to neutral as well. +2, -2. This is good. Now, when you get to this point, we're in a good place because we have 1/2 oxidized and 1/2 reaction reduced. We said oxidation involves losing electrons, and that should be the oxygen half reaction. And reduction involves gaining. That should be the manganese half reaction. Yep, it's gaining electrons. The only problem is that we're not transferring the same number of electrons. And so for that, I'm going to have to fix both of them. I've got a 5 and a 2, so we're going to have to go for 10, huh? We'll take all of this times 2 and all of this times 5. We have to balance the electron transfer. This then will become 10. Oh, brother. 16 hydrogen. 2 permanganate, 2 manganese, and 8 water. Then the second half all gets multiplied by 5. And then, yep, here's going to be my 10 hydrogen and my 10 electrons. Last thing we do then is simplify the best we can. For sure, we can cancel out the 10 electrons. Other things that I would look for would be water and hydrogen. We had water in the first half reaction, but not the second. But I can simplify my hydrogen. There are 16 on the reactant side, and then 10 on the product. So we could get rid of those, and then we could bring this to a 6. And then I think we got it. In any order, somehow on the reactant side, there are 6 hydrogen ions. There are 2 permanganate. There are 5 hydrogen peroxide. And then on the product side, I'll have 2 manganese ions, 8 water, and 5 oxygen. Again, you probably didn't really notice it at the time, but as you titrate, it does give off like little teeny tiny bubbles. Sometimes it almost just looks a little bit like 7-Up. That it is the oxygen coming off of the hydrogen peroxide. As we titrated them, we saw a color change. This should have gone from the purple permanganate to the kind of pink manganese +2, like a real pale pink. Fantastic. Okay, so we got 1, we got 2. Moving on, let's do some calculations. Moles of permanganate ion used. Okay, so often people hear titration and they freak out. But here's again why it's good to just go back and revisit this concept of a titration. All it is a laboratory method where we react things until we hit the ratio in the balanced equation. When we did the acid-base titrations, we kind of knew the pH range in which we would hit the equivalence point. And here we didn't need an indicator. We were just looking for the color change on the ion. But the calculations are just stoichiometry. Equivalence point, end point. It just means that we hit the balanced equation, the ratio from the balanced equation. Moles of permanganate used. When I ran this, I needed about 12 milliliters of permanganate, which, oh, it must have got cut off. In number 3, I'll put that up on top. In number 3, it was just the volume of permanganate used. Volume of permanganate. And so if you only ran one trial, it's just the volume delivered. If you went super geek and ran multiple trials, you could average them. Unless you feel like one trial was really bad, then just go with the trial that you feel is better. Mine was about 12. I used about 12 milliliters. Which then brings me to number 4. the concentration of the permanganate was always 0.025 molar. MnO4 minus. It's in the data section. They asked you, like, what was the concentration? So it was just written on the beaker. It's in the material section. It was 0.025. Molarity equals moles per liter. I used 12 milliliters, or 0.012 liters. All right, so if I cross multiply, I'm looking at not a lot, 0.000. I'll go 3 sig fig moles of permanganate. Titrations are just stoichiometry. It's solution stoichiometry, where there's one solution that I have to be able to find moles of. It's the solution that you're adding from the burette. That's the solution of known concentration. I knew it was 0.025 molar, and then I know the volume used. Then, since we can calculate moles, we can use that to figure out moles of a solution that we're trying to study. We're studying the hydrogen peroxide, and so if I know moles of one reactant, moles of permanganate, now I can just use the ratio in the balanced equation to get moles of the unknown. This was 2 moles of permanganate for every 5 moles of hydrogen peroxide. That is just the ratio from the balanced equation. Okay, so this gives me 0.00750, teeny tiny moles of H2O2. Awesome. Now from here we could do a couple things. If I wanted, I could turn this into molarity, moles per liter. So I could say, okay, here were the moles, and I used a 1 milliliter sample, and so I could figure out the molarity. If it were, oh gosh, like an unknown acid or something, we could find its molar mass. I could say, okay, this is the grams that I used, and here's the moles. Molar mass is grams per mole. Or in this one, we'll do something kind of similar, but we're going to do a percent by mass. So I know the moles. Number 6 wants to know how many grams of hydrogen peroxide were titrated. I've got 0.000750 moles of H2O2. And I'm just going to change it from moles to grams. Every 1 mole should have the mass on my periodic table. 2 hydrogen, 2 oxygen is about 34.02. Let's see. So we might have different moles to start with, but we'll all use the same molar mass. We'll all have the same ratio in the balanced equation. I got like 0.0255. Here's grams. Fantastic. So there'll be some similarities. And number 4, we all had the same initial solution, so it was the same concentration. Number 5, the ratio is always the same. And then in number 6, the molar mass is the same. This is all titration calculations are. Now obviously it gets into a little different world when we start graphing and looking for the pKa so we can estimate the Ka. Oh my gosh! But we don't have to do that here. Okay, cool. So then finally, I got to remember this number, 0.0255. And number 7, assuming that the density of the peroxide solution is 1 gram per milliliter, calculate the percent hydrogen peroxide by mass in the solution. Okay, so percent H2O2 is just mass of the hydrogen peroxide. That's my answer from number 6. 0.255 grams divided by mass of the solution, which we really did use 1 milliliter. And so they're saying the density is 1 gram per milliliter. 1 milliliter should be 1 gram of solution. Multiplier by 100 to get a percent. Oh, wonderful. It's about 2.55% by mass of hydrogen peroxide. Now, often we do molarity as a way of measuring the concentration of a solution, but you can also do this percentage. You'll see that a lot with maybe it's a 10% sugar solution or a 5% salt solution. On the bottle, the hydrogen peroxide is said to be 3%. So the theoretical is 3%, which then means that it's 97% water, 3% hydrogen peroxide. I kind of purposely grab a bottle of peroxide. Whenever we do this lab, I grab a bottle that's been open for a while, because hydrogen peroxide does just have a tendency to decompose on its own. And that's why it's stored in those brown bottles, because it's not as stable as water. And just ultraviolet light will get it to naturally decompose. So I always grab an old bottle because I think it's interesting finding that it's not what it's supposed to be. That over time it does just naturally decompose and form water. But this isn't too bad. So hopefully you're like somewhere around a 3%. And finally, number 8. In number 8, it says, if an insufficient amount of acid is added in step 9 of the procedure, some of the permanganate ions will be reduced to a black solid of MnO2, manganese dioxide, instead of the manganese plus 2 ion. That was supposed to be the light pink ion. And ironically, some of us just proved this in the lab. When we ran this, there were a couple times where a group would be like, oh my gosh, it's turning brown, it's all cloudy and weird. And we said, oop, just run it again. Insufficient amount of hydrogen. So what happens is if I go back to my balanced equation, instead of forming this, which is the pink, that's what we wanted, you form MnO2. Oh. They want us to rebalance the reaction. Interesting. And then we want to look at how that changes the mole ratio and how that affects the amount of potassium permanganate needed to reach the equivalence point or the end point. Okay, so our hydrogen peroxide half reaction will be exactly the same. That is not changing in any way. The only thing that we're going to change is the manganese half reaction. So if I go back to this guy, I'm going to start off with the exact same hydrogen peroxide. It would be the H2O2 forming oxygen. And then we said all we had to do to balance it was add the 2 hydrogen ions. And then we'll see if we need to fix that any further. Then I'm going to put in the permanganate, but it's going to form MnO2 instead of the manganese ion. Okay, so step 1, balance the manganese, which there's 1 on each side. Step 2, balance the oxygen by adding water. Step 3, balance the hydrogen by adding hydrogen ions. Okay, so I will need 4. Excellent. Now I gotta check the charge. Actually, I should check the charge on both of them, huh? So the first one, neutral on the reactant. I'm gonna need 2 electrons. Ooh, the second one is neutral on the product side. So on the reactant side, I've got a +4 and a -1. That's a +3. We got to make it neutral. 3 electrons. Fantastic. Okay, so before I can add them together, the electron transfer is not the same. So we got to fix that. Oh, brother. We got to go for 6, huh? Times 3. It's so much work. Times 2. All right, so 3 and a 3 and a 6 and a 6. And then this is going to be 6. 2 times 4 is 8. 2, 2, 4. Please make it stop. And now we can add them together. And simplify by canceling any like terms, which for sure would include my electrons. Waters I still don't have on both, but I can simplify my hydrogen. 6 produced, 8 on the reactant side. So we could get rid of these 6 and bring that to a 2. All right, let's see if we got it. In any order, here on the reactant side, I'm left with 3 hydrogen peroxide, 2 hydrogen ions, and 2 permanganate. On the product side, in any order, I have 3 oxygen, gone, 2 of these manganese dioxide, and 4 water. Fantastic. I think we got it. Does it change the mole ratio? You bet. The original was 2 permanganate. Yeah, it was 5 hydrogen peroxide. And now the new ratio, I've got 2 permanganate and 3. Yep. 3 hydrogen peroxide, H2O2. Yes, it changed my ratio. How will that affect the volume? Part C. How would this affect the volume of potassium permanganate needed to reach the end point? Okay, the end point, when I end a titration, it's when I'm at the stoichiometric ratio. Think about it this way. Originally, two moles of permanganate, MnO4, would react with 5 moles of the peroxide, H2O2. Well, now in the new reaction, if I wouldn't have used sufficient acid, now 2 moles of permanganate only react with 3 moles of hydrogen peroxide. If you think about it this way, if you say it this way, I think it makes more sense. That in the first reaction, every 2 moles of the permanganate would have reacted with 5 moles of the peroxide. But now in the new reaction, 2 moles of permanganate will only react with 3 moles of the hydrogen peroxide. So if I didn't use sufficient hydrogen, more permanganate would be needed. It's going to seem as though more permanganate will be needed. because this time in the second trial, I can only react 3 moles of the hydrogen peroxide. And if we use the same hydrogen peroxide, there would be the same amount of H2O2 in the original solution. But now I'm going to react less of it per mole of permanganate. It's supposed to be a 2 to 5 ratio. It would seem as though I would need more permanganate ion, or more of that purple solution. And then finally comes the conclusion. In the conclusion, you're going to write a little paragraph where you'll just kind of reflect on what might be some common errors. Now, obviously, one error that's kind of built into this is that the peroxide probably isn't 3% just because it was old. I purposely kind of set you up for failure. I used an old solution. Think about what it means to go beyond the equivalence point. Did you stop at a nice pale pink, or did you add a little too much? Obviously, we'd like to run multiple trials, if time would have allowed. So you'll write a little paragraph conclusion, and then this will be wrapped up. But we do have to at least be aware of the fact that you can titrate beyond just the world of acids and bases. It is really just a lab procedure that requires us mixing things together and somehow being able to indicate when we've hit the ratio from the balanced equation. And with a redox titration, if you have a transition metal ion, they often change color in solution. And then that's kind of like a natural indicator.